Okay, so last week we started looking at force position method, also known as the regular forcing method, where we between the values, it's a bracketing method. We draw a chord, then we try to find out where the chord cuts, then we use that position to start moving things around like that. Okay, so we are going to continue looking at examples of how, actually two examples of how we actually use this method and see how it works. Then after that, we are going to create a program which is going to operate based on how this algorithm works. So here we have got an example. Example number one: find the root of the equation x to the power x squared minus 10x plus 2 equals to plus 23 equals to 0. As you can see, this is a quadratic with the force position method in the interval 6.0 and 6.8. So the first thing you notice when it comes to using the force position method is that the interval is going to be small. Usually the interval is going to be 1 or less than 1. The thickness of the initial interval you're going to have is going to be 1 or less than 1. The reason why that's the case is because as much as this method is fast, sometimes depending on what kind of function you have, it can quickly become slow. It can kind of like slow down even though eventually you're going to get the answer. So usually we start with an interval which is small enough. Like in this case, the thickness of the interval, as you can see, is between 6 and 6.8, which is just 0.8. Okay, so in our case here, our A is the lower bound. That's our A, 6, and our B is 6.8. So basically, that's what we're showing here. Now, since this is a bracketing method, I think we need to inform the rest of your other friends that we go to class. Okay, so since this is a bracketing method, we have to convince ourselves and check if there's a solution in between in this bracket, because that's what you do with any bracketing method. You have to check that there's a solution in this bracket. Let me just say, okay, so since this is a bracketing method, when you are dealing with any bracketing method, whether it's bisection, which we looked at in third year, and this one which you're looking at now, you have to be sure that in this bracket you're looking at, this bracket you have been given, there is actually a solution in that bracket. So you can't just start doing things without being sure whether a solution exists in this bracket or not. Are we clear? You have to make sure that the solution exists in the bracket you've been given. Like in this case. In this case, we don't have a function because I was doing things with pencil. There is no plot for us to see that there is actually a solution in this bracket. So you need to check physically to see if there is actually a solution in this bracket. So your first task is to check if a root or a solution exists in the bracket 0.6 and 6.8. So how are you going to do that? So in this case, your A is 6.0, your B is 6.8. So you need to find out what is f of A and what is f of B. So you have to evaluate the function, this function x squared minus 10x plus 23 at A, and how much does it give you at B. So f of A, that's going to be f of 0.6, that's going to be 6 squared minus 10 times 6 plus 23, that's going to be negative 1. Then f of B, your f of B is going to be f of 6.8, that's going to be 6.8 squared minus 10 times 6.8 plus 23, that's going to give you 1.24. So at A, the function is minus 1, which is negative. At B, the function is 1.24, which is positive. Then how do we know that a solution exists in this particular interval? So we evaluate this product. We work out the product f of A times f of B. So you work out the product f of A times f of B. So in this case, f of A times f of B, that's going to be minus 1 times 1.24. That's going to give us minus 1.24. This minus 1.24 is negative, which is less than 0. So if you are given a bracket, in this case A and B, then you work out the value of the function at A, then you work out the value of the function at B, then after you find the value of the function at A, then you find the value of the function at B, then you multiply the values of the function f of A times f of B. You get your product. If the product is less than 0, then that means that there's a solution in this particular bracket. Okay?
Morning, sir.
Yes.
Good morning, sir.
Yes. Go ahead.
There's someone which likes to get.
Okay, I've admitted them. So if the product is less than 0, so you multiply f of A times f of B, which is the lower interval of the bracket and the upper interval of the bracket. You multiply the value of the function at the lower interval of the bracket, you multiply the value of the function at the upper interval of the bracket, then you do f of A times f of B. If you get a product which is negative, meaning that it's less than 0, then it means that there is a root between that particular interval, because as you can see, at A our function is negative, at B our function is positive, so that means that our function has crossed the x-axis. Is that clear? If your product of f of A times f of B is negative, like in this case, it means that your function has crossed the x-axis. So in this case, it was moving from negative to positive, so it has crossed the x-axis in between 6.0 and 6.8. If your product of f of A times f of B is positive, it means that your function has not crossed the x-axis in that particular interval. So if you're going to bracket, then you might work out this product, then it comes out positive, then it means that there is no solution in that particular interval. So since our product f of A times f of B is less than 0, a root exists between A and B. So we can proceed to carry out our first position method. So what do we do with first position? So we start with the first iteration. For k equals to 0. For k equals to 0, we estimate what the root is going to be, which is our C, our guess root C, using the following formula. C is going to be equals to B multiplied by f of A minus A multiplied by f of B divided by f of A minus f of B. So this is the expression we use for finding out what our guess root is going to be with a regular with first position method. This is the expression we use. We derived this expression last week, so now we just need to use it. So in our case, A is 0.6, f of A is minus 1, B is 6.8, f of B is 1.24. So we do the substitutions. Where there's B here, you put your 6.8. Where there's f of A, you put your minus 1. Where there's A here, you put your 6. Where there's f of B, you put your 1.24. Where there's f of A here, you put your minus 1. Where there's B here, you put your 1.24. When you do that, you end up with the following expression. You end up with C is equals to 6.8 minus 1 minus 6 times 1.24 minus 1 minus 1.24. So this, when you do that, it's going to give you C is equals to 6.357 142,857. So this is going to be your first guess solution. How good is this solution? So we work out what is the value of the function at C. So we evaluate f of C. So when we evaluate f of C, f of 6.375 142,857, that's going to be f of C, which is this. So it's going to be our C, which is 6.375 142,875 to the power 2 minus 10 times 6.375 142,875 plus 23. We are going to get this. We're going to get minus 0.158163,268. Okay, small, but it's not exactly equals to 0. Since a solution in this case, when we were coming up with the formula, what we agreed to be a solution was a value of C which would make our function approximately equals to 0. So in this case, as you can see, our C is this much, minus 0.175163,285. Okay, the other thing we do apart from finding our C, which is not very good in this case, we check whether there is a root between our A and our C. We check if, since we have found the root C and we are doing a bracketing method, so which means there has to be a way of adjusting our bracket. We check if a root exists between A and C by working out this product f of A times f of C. Now, as you have seen, when you work out a product f of A times f of C, if this product f of A times f of C, we multiply between this particular function, these values, the value of the function at A and the value of the function at C, if we multiply their product, then it comes out negative. Then it means that a root exists in that particular interval. If it comes out positive, then it means that a root does not exist in that particular interval. So in this case, we multiply f of A times f of C. F of A we know is minus 1, and f of C is what you found here. This is f of C, minus 0.158, 163, 263. So we multiply f of A, which is minus 1, times f of C, which is minus 0.158, 163, 253. So this is a negative number being multiplied by a negative number. So what you're going to get is a positive number. So you're going to get f of A multiplied by f of C, which is equal to 0.158, 163, 265, which is greater than 0. So it's positive. So the product f of A times f of C is a positive product. If you have a positive product, then it means that between A and C, there is no solution. Okay, now one of the things I want to highlight with a regular force position method is that once the method starts, you will be squeezing the bracket only from one direction. It's not like bisection where you squeeze from this side, you squeeze from the left, you squeeze from the right, then you squeeze from the left, or right, then left. With the force position method, you always squeeze from one side until you come up to a value of C which makes your function approach 0. Okay, so in this case, as you can see, our f of A times f of C is positive, which means that between A and C, there is no solution. So if between A and C there is no solution, then we are going to make our A, or are going to make our C become the new A, and they're going to make the value of the function at C become the value of the function at A. So this C, which we found to be 6.357,142,857 becomes our new A. So we do this. We make our C become A. Then we make the value of the function at C become the value of the function at A. And our value of the function of A is going to become our minus 0.158, 163, 265. Is that clear?
Yes, sir.
Next, we repeat the process again. We do it for k equals to 2. So our f of A, our A has changed, and our f of A has changed. So we work it out for k equals to 2. We calculate a new guess value, C. So C is going to be equals to B, f of A minus f of B, then divided by f of A minus f of B. So our new A is 6.357,142,875, and our f of A is now minus 0.158, 163, 265. Our B is still the same. That is a good advantage with bisection. You only be squeezing from one side. The other bit will remain whatever it is. So our B is still 6.8. Our f of B is still 1.24. So the only thing which will be changing now is going to be just A and f of A, since you only squeeze from one end. So your B, you put your B there. So here, if you put your B there, that's going to be a 6.8. Your f of A is what you have here, minus 0.158, 163, 265. You put it there, then minus your A, which is what you have here, 6.357,142,875 times f of B, which is 1.24. Then the value of the function at A, which is minus 0.158, 163, 125 minus 1.24, which is your f of B. When you do that, you're going to come up with a new value of C. So your C now is going to be C is equals to 6.403 6.407 239,819. So previously your C value was this one, 6.357142857. Now it becomes 6.407239819. How good a solution is this? So you evaluate the value of the function at C. So the value of the function at C, that's going to be f of C. So that's going to be your 6.407239819 to the power 2 times minus 10 times 6.407239813 plus 23. So you're going to end up having your value of the function being equals to minus 0.019 minus 0.019 676,092. So already from just the first solution, which wasn't good enough, now we have got something which is good enough, because our function is now minus 0.019 something. Are we clear?
Yes, sir.
Yeah. So starting with a smaller bracket, as we do with regular first position method, and also only squeezing from one end, makes things a bit faster. So now that we have our function, the value of the function is known, which is this, then we can check if between C and F, between C and A, there's a solution. So in our case, f of A and f of C. So you check between A and C. So you work out this product f of A times f of C. So your f of A, if you look, your new f of A is this, minus 0.158163,265. That's a new f of A. So you're always squeezing towards the solution. With the first position method, you're always squeezing towards the position. So this is your f of A. Then your f of C is this one, minus 0.19673,092. So here you're multiplying a negative number times a negative number, so that should give you a positive number which is greater than 0. So basically that tells you that between A and C there is no solution. So if between A and C there is no solution, then since the product f of A times f of C is greater than 0, so between A and C there is no solution, then your new value of C, you can make your new value of C become your new A. So your A now becomes 6.407239891. Then your f of C becomes the f of A, which becomes minus 0.096676092. So with this new A and new B, then you can work out a new C. So that's where we come to for k equals to 3. So you can work out a new C. For k equals to 3, working out for a new C. So we calculate a new C as follows. C is going to be equals to B, f of A minus A, f of B divided by f of A minus f of B. Our new A is 6.407239819. Our new f of A is minus 0.196676092. This bit here remains the same, because with first position you always squeeze only from one end. So your B is 26.8, your f of B is 1.29. So when you make the substitutions, where there is B, you put your 6.8. Where there is f of A, you put this thing here. Where there is A, you put this guy here. Where there is f of B, you put this guy here. Where there is f of A, you put this guy here. Where there is f of B, you put this guy there. Is someone trying to get admitted? Okay. You put that guy there. Then you work out what your new C is going to be. So your new C now is going to become, so you've got 6.8 minus 0.19676,098 minus this bit here times 1.2, then whatever this new f of A is minus f of B. So you're going to get yourself a C which is equals to 6.413374718. So it's moving slowly towards the solution now. So the first thing about what you notice about regular FOSI is it quickly moves towards the solution. Okay, once it reaches the solution which is sufficiently okay, then things tend to slow down. It will continue moving towards the solution slowly, but it has already reached. It's like someone who you are running a 100 meter. You are running 100 meters, so you run very fast. When you reach 95 or 98, 97 meters there, then you start crawling. So it starts crawling towards the solution. Okay, so basically you can continue doing this, but you need to realize that sometime after you reach a solution which is sufficiently okay, the solutions you're going to get are going to be changed very slowly from the other ones, because already what you see, what we have, this is our new C. It is 6.413. That's what we have here. We have got two other C's. The first one we got was this one, 6.357. From 6.357, so there is a 6 there, then it moves to a new C, which is 6.407. Okay, something. Then the new C we find, you notice that the 4 stops changing. The 6.4 stays place. The only thing which has changed is the 07 after that. So you notice that now we have 6.41. So the 4 has stopped changing. So it's somewhere 6.4, but the 4 has stopped changing. So the moment once the 4 stops changing, the next thing which is going to stop changing is going to be the 1. So the 1 will remain fixed. So it's going to be 6.41. Then the other numbers, as you keep on doing this process, the other numbers will continue changing, but the whole thing is going to change very slowly. So in all effect, basically, the solution is not going to change from 6.4. Most likely, it's not going to change from 6.41. Are we clear? So let's see. So when you do this with 6.4, okay. So with 6.413 here, then we check if there is a solution. Then you work out the function, the value of the function at this 6.413 something. So f of c, which is f of 6.413, 374, like that. When you do that, you end up having 6.413, 374, 718 squared minus 10, 6.413, 347, 718 plus 23. You get this number. You get minus 2.371906,837 times 10 to the power minus 3. This is a very good solution. This is practically equals to 0. Are we clear? So we could stop here. We could stop here where we get this as our solution. If you want to go a bit further, you say, okay, fine, I want to, of course, check if there is a solution between A and C. Of course, you're not going to have a solution because your C is negative. Your A is also negative. So when you work out f of A times f of C, so you're multiplying negative times negative, you're going to get f of A, your f of A up here, where you're working out your C. When you're working out your C, this C you found here, your f of A, as you can see, your f of A is negative. Your f of A is negative. Then your f of C, which you've just worked out here, f of C here is also negative. So you're multiplying negative times negative. So between A and C, when you multiply those, you have a negative number multiplied by a negative number, you get a positive number which is greater than 0. So basically that is telling you that between A and C there is no root. So you squeeze. Okay, so your C now becomes a new A, and your f of C now becomes a new f of A. So your new A now becomes 6.413, 374, 718, and you do this like that. You can now work out for k equals to 5. For k equals to 5, you can work out a new c. So your c is going to be equals to b. F of a minus a, f of b, then f of a minus f of b. So in this case, your a is now 6.413,374,718. Your f of a is minus 2.371,906,378 times 10 to the power minus 3. Then your b is 6.8. F of b is that. You make the substitutions here. You are going to get your c being equals to, you substitute here where there is the responding things. You're going to get your c equals to 6.41414122112,875. So what I'm trying to show you is that now you notice in the first bit the 4 was in place, now the 1 has stopped changing. So basically the answer is not going to change from 6.41. Are we clear?
Yes, sir.
Yeah, the answer is not going to change from 6.41. So the more you do this, the more your answer hardly changes. It's just being, some numbers are just becoming fixed. So the more they become fixed, the more your answer doesn't change anymore. But you can continue doing that until all these numbers stop changing. So you're with a fixed what the root is supposed to be. You work out what your function is at this particular value. So when you do that, so you're going to end up with f of 6.414112854. When you do that, 6.414112854 to the power 2 minus 10, then 6.414112854 plus 23. You're going to get this. So this is basically minus 2.848367894 times 10 to the power minus 4. I think this is practically equals to 0. For this method, once you reach a level like this is good enough, because it's not going to, you are not going to gain much by proceeding. Are we clear? The numbers will not change very fast. They will just be from what we have here. Next, it will just be the 4, which is going to become solid. So there is no room for maneuver anymore. It can continue happening, but room for maneuver anymore is going to be very, very little. So the thing you're supposed to be aware of when it comes to force position is, force position, if you've got a good function which responds to force position, like we have a quadratic here, it will quickly move you to the solution, it will quickly converge to the solution, then it will slow down. But if you've got a function which is flat, which seems to be flat, then it is going to even become worse. It will move, it will crawl. It's like you're trying to cover 100 meters crawling. So there has to be, you have to be very careful what kind of functions you choose to use this method with. With bisection, things will just happen, whatever, but it's very slow. But force position is a bracketing method which is faster than bisection. But it depends also on what kind of function you have. If your function is flat somewhere, then it could land you in a bit of a problem. So you proceed, what am I doing here? I think I proceed to do the same stuff this side. That here, then I think I do a final thing, final solution. I've got this here, then I work out a final solution here. In our final solution with this bit here, which we already have, in our final solution you see that our 4 is now solid. So you've got 6.414. The 4 has stopped changing. The 4 was there in our previous solution, which is this, and now it has stopped changing. So there is nothing really, any more improvement you're going to get. The only thing you're going to get are numbers becoming fixed and fixed and fixed like that. Are we clear? And of course, if you work out the value of the function at this final value of c, we have worked out 6.414,201,478. You see that even the increase we have got, it's just times 10 to the power minus 5. The previous one we had was for our C value. The previous one we had was times 10 to the power minus 4. So we haven't got much. We are gaining very little and little the more we do this. Here it was times 10 to the power minus 4. So when it reached times 10 to the power minus 4 for our C, then here it's 2 times 10 to the power minus 4 for our C. Then it simply, the more you do it, you are just going to be gaining, you're not gaining much basically, times 10 to the power minus 5. Where is that? Here, times 10 to the power minus 5. So we gain very, very little by doing this method over further and further and further away. Are we clear? Is that clear?
Yes, that's clear.
Yeah. So first position can be as faster as Newton-Raphson method or second method, but you need to stop quickly. You need to know when to stop. And you need to know when to stop. What kind of tolerance are you able to accept? Okay. Any questions? Okay. We have another example. Example number 2. Find the root of the equation cos x minus x plus 1 equals to 0 with the first position method in the interval 0.8 then to 1.6. When are we having our next class? I don't know if we're going to finish this in time because I've got 20 minutes anyway. So let's push. So again, so we have been given this first position method, like I said earlier, it's a bracketing method. So if it's a bracketing method and they've been given an interval, you have to check if there is a solution in this particular interval you've been given. The other thing I want to point out here is that we are using a trigonometric function. So if you're using a trigonometric function, then it means that you have to make sure your calculator is set to accept angles in radians. If you don't change your calculator to accept angles in radians, your calculator is going to think it's accepting angles in degrees, which is not correct in this case, because these numbers we're using, 0.8, 1.6, these numbers have got units of radians, they are not degrees. Are we clear? Any number, any real numbers you have, 1, 2, 1.5, 1.8, if it's just a number like that, that number has got units and those units are radians. Are we clear?
Yes, sir.
So when you've got a function which has got some trigonometric thing in it, you have to set your calculator to accept angles in radians. So on the display of your calculator, instead of degrees, there has to be an arrow there. Okay. So with your calculator set to accept, if you don't set your calculator to accept angles in radians, then you're going to get everything wrong. Okay. So we check. In this case, our lower bracket A is 0.8, our upper bracket B is 1.6. As you can see, the difference between 0.8 and 1.6 is just 0.8. So the first requirement when you are using, I'll mention it again, when you're using this method, first position method, you have to make sure that the bracket is small. Your bracket has to be small. If your bracket is large, then this thing is going to take longer to work out. Okay, so make sure that your bracket is quite small. So in this case, it's just a thickness of 0.8. So your A is 0.8, your B is 1.6. So we evaluate the function at f of A and f of B. So in our case, f of A, that's going to be f of 0.8, that's going to be cos 0.8 minus 0.8 plus 1. So you're going to get this thing here, 0.896706,709. Then f of B, which is cos f of 1.6, that's going to be cos 1.6 minus 1.6 plus 1. So you're going to get minus 0.629919,522. So you've got the value of the function at A, you've got the value of the function at B. As you can see, the value of the function at A is positive, the value of the function at B is negative. Then you want to check if there is a root between A and B, you work out the product f of A times f of B. So in this case, it's f of a times f of b. That's going to be 0.896706 multiplied by minus 0.6291999522. So this is negative. This is positive. That's negative. So you're going to get up with the product which is negative, which is less than 0. So this less than negative product of f of a times f of b is showing you that between a and b, our function, which at a had a positive, was positive valued, and at b is negative valued, has crossed the x-axis. That's how you know that there is a solution between a and b. Always check this. Always check. Okay, always check if there's a solution between a and b. Otherwise, you're going to waste your time. Okay. Next, since we have got our a and b, and we know that there's a solution between a and b, we can work out our guess root for k equals to 0. So here, for k equals to 1, our guess root c is going to be b times f of a minus a times f of b divided by f of a minus f of b. So our a is 0.8, our f of a is what we have here, our b is 1.6, and our f of b is what we have here. When we do our substitutions, we end up having b is 1.6, so you put a 1.6 here. Our f of a is what you have here, we put it there. Our a is this one, 0.8, you put your 0.8 here. Your f of b is what you have here, you put it there. Then at the bottom, divide by f of a, which is this here, f of a, then minus f of b, which is negative there. So basically, you've got a negative, that's going to turn out to be positive somewhere there. So when you do that, you end up having your c being equals to 1.270,124,148. Remember, our bracket was 0.8 to 1.6. So our c is 1.270,124,168. So where is what is the value of the function at c? So the value of the function at c, remember at a our function is positive. At b our function is negative. So depending on what we find at c, if c is positive or negative, then it's going to dictate what you're going to be doing the rest of the time. So the value of the function at c, which is cos 1.20124,148, that's going to be cos 1.20 here, cos 1.270,124,148 minus 1.270,124,148 plus 1, you end up having this 0.026038,148. So basically, our function at c is positive. Our function at a is positive, our function at c is positive, our function at b is negative. That's what you have. C, our function at c is positive. So what we have here, basically, you can clearly see that our function at a is positive, our function at c, which is somewhere in the middle, not exactly in the middle, but somewhere in the middle between a and b, it's also positive, and our function at b is positive. So you can see that between a and c, there is no solution, since the function between a and c is positive. So the solution must be between c and b. Are we clear? Are we clear? So here, next we check if a root exists between a and c by evaluating the product f of a times f of c. So f of a times f of c, f of a is this, f of c is that. So as you can see, positive times positive, you get yourself a positive number which is greater than 0. So if you get yourself a positive number, then it means that between f of a times f of c, there is no root. So if between a and c, there is no root, then you make your c become the new a. So your c becomes a, which becomes 1.270,124,148. And f of c becomes the f of a, which becomes 0.026038,146. Then you move on. For k equals to 2, you work out a new c. So your new c with your new a and f of a, your c is going to be equals to b minus f of a minus a f of b divided by f of a minus f of b. Your new a is 1.270,124,148. 148. Your f of a is now 0.026038. Your b remains the same, unchanged. Now we are squeezing from a, going this way, going to the left. We're squeezing from the left until we get to a value of c which slowly begins to remain unchanged. Then your b is 1.6, your f of b is this much. So you substitute your values of c is equals to 1.6, 0 point this bit, your value of a, then so b times the value of a, then value of a times the value of b, then your value of a, f of a is this, minus your f of b, which is that, negative, you do something there. Then when you do that, you end up having c is equals to 1.283232916. One thing you notice already is that our first c gave us 1.2 something. Our first c 1.27, 1.270, 14, whatever it is. Our next c is just 1.2 something. The 1 has remained fixed. The 2 has also stopped changing. So the solution is somewhere at 1.2, because already with our next c, the 1 has stopped changing, the 2 has stopped changing. The only thing which has changed is what comes after the 2 in this case, the 7. Are we clear? So the answer is somewhere at 1.2. Is that clear? Hello? You have to see how the numbers are changing. So already we can see that the 1 has stopped changing, the 2 has stopped changing. So the answer is somewhere at 1.2. So when you work out you evaluate the function, the value of the function at c at 1.283 232,912. So you do that, you're going to have, of course, 1.283 232,912 minus this bit plus 1, you end up with this. Already you can see you have a very good value of the function. It's already 3.836 times 10 to the power minus 4. This is a very good solution already. Okay, this is what we have here, is a very good solution already here, giving us this value, because this is practically equals to 0. Okay, so we check if a root exists between a and c as by evaluating the product f of a and f of b. Our product f of c is positive, f of a is also positive. Our f of a is this one here. Our f of a is positive. This is our f of a. So positive times positive just gives you positive. So between a and c, there's no solution. So a positive times a positive gives you just a positive product, which is greater than 0, meaning that between a and c, so the product f of a times f of c is greater than 0, meaning that there's no solution between a and c. So if there's no solution between a and c, then you make your c become a, then you make your f of c become your f of a. So your c, your new a now becomes 1.283232912, and your f of c, your f of a now becomes this. It becomes f of c. So you can work out a new root for k equals to 3, your guess value for the third time. When you do it for the third time, so you can work out a new c. When you work out a new c, so you've got your new a, which is this, you've got a new b, your new f of a, which is that, but your b and your f of b remain the same. When you do the substitutions, you put in there, you are going to get your new c. So with your new c, you notice something. Your previous c was 1.28. This is your previous c, 1.283. With this new c you're working out, the 8 now doesn't change, has stopped changing. It's actually not the 8, the 8 and the 3 have stopped changing. These two guys, the 8 and the 3, these two digits have stopped changing. 8 and 3 have stopped changing. So your c is now 1.283. This one then the 2, then the 8, and the 3, we are sure about, because these digits have stopped changing. Are we clear? The other ones which have not stopped changing, which are these other ones. But since we have got enough numbers up to 3 decimal places which have stopped changing, we evaluate what the function is at this particular thing. At this particular C, when we do that, you end up having f of 1.283 425,927. You put in cos 1.283 425,927 minus 1.283 425,925 plus 1, you get you 5.5137,00543 times 10 to the power minus 6. That is good enough. This is very, very good enough. This is practically C equals to 0. Are we clear? Are we clear? So you have to see what your value of the function is. Yeah. You can check if you want to be more adventurous like I did to see. But right when you reach this point, there is really no reason for you to go any further. But if you do that, how much you're going to gain really, if you check between A and C, if you're going to have anything, so you would, your A is positive, your C is positive, there's nothing between A and C. So basically, there is no root between A and C. If you do this, like this, then you work out the final C from this bit. So your A, you now make your C become your new A, and your f of C become your that, which is what you have here. Then you work out the final value of C. You work out the final value of C based on a new A in this bit here. So you would A equals to 1.283 425,927. Then your f of A equals to this, then your B is 1.6, and that you substitute in here. When you do that, you are going to end up having a final value of C, which is equal to this 1.283,428,70 that. So you've got a 4 here, and I think there was a here. So you have got this first number, the 283 is fixed, and 42 become fixed now. This one also becomes fixed. The only thing which is going to change is the 5, which becomes 8, and like that. So basically you've got these 5 numbers after the decimal point, 5 digits after the decimal point being fixed. If you've got 5 digits after the decimal point being fixed, you evaluate the function at this particular point, you end up with what we have here as the value of the function being equals to at C being equals to 7.9820682 times 10 to the power minus 8. So we are very, very accurate this time around with this particular one. Are we clear?
Yes, sir.
Yeah. So we are done with this chapter 1. Solutions to nonlinear equations with forced position method. So this chapter is done. The next thing we're going to look at is a solution to systems of linear equations using a method called Gauss-Seidel method, iteration method. So basically, we are first of all continuing with, I think the way we started the last year course, we used different methods, but since we couldn't squeeze all the other methods in this in what we did last year, we're just picking other important methods which you might need to know how to use. Okay, so we're going to proceed. The first few chapters will proceed like what we did last year, except using different methods. Then the other things are going to be introduced which are completely not absent in the other course. Okay, so this part is done. You should expect an assignment which is going to be posted on Moodle, and also which people should submit. Those of you who are able to access Moodle, you will submit through your Moodle. The other people who are not able to access Moodle, only those who are not able to access Moodle will have to submit their stuff through my WhatsApp. Okay, so the assignment is going to have 2 questions, and Yeah, you should get that during the course of the week. So I'll see you tomorrow. I think when is our last class of the week? Is it tomorrow? Yeah. So see you tomorrow where we are going to introduce what is referred to the Gaussian Seido method for solving linear systems of linear equations. Okay. So here we are done.